Good day everyone, my name is Shurland Balliram, the presenting and second author of the paper E04 titled Experimental and Numerical Vibration Analysis of Printed Circuit Boards. Printed circuit boards, or PCBs, are modules which are incorporated in a wide range of industrial equipment and machinery. PCBs that are situated in dynamic environments may be prone to failure from excessive cyclical stresses arising from harmonic or random vibrational sources. The ability to numerically model and predict the dynamic behavior of PCBs and associated components is therefore a valuable tool for analysts concerned with PCB reliability. Experimental vibration analysis and the finite element method are used to investigate the changes in resonant behavior of a PCB as the mass, location, and stiffness of electronic components vary. Literature review and objectives. These are the various methods authors across the world utilize to predict the vibration response of PCBs, solder joints, or electronic components. So here 2000 predicted the vibration frequency response of a heavy electronic component mounted on a PCB using excessive mathematical calculations. However, Shaker 2016 carried out a response spectrum analysis of a PCB subjected to shock loads. Likewise, Anuhar 2012 did a modal characteristic study of a CEM-1 single-layer printed circuit board using experimental modal analysis. In this paper, the objectives are as follows. Firstly, to modify and build a printed circuit board with solid electronic components such that it represents a generic circuit in a typical industrial application. Secondly, using a commercial finite element software package, simulate models of the circuit board and the connected components to predict the vibration response levels due to harmonic and random excitational sources. Thirdly, to compare the theoretically obtained vibration levels with experimentally determined values to quantify the accuracy of the simulated models. Lastly, to investigate the influence of electronic components on the natural frequency and mode shapes of the printed circuit board. Methodology. Description of the PCB. The selected printed circuit board functions as an adjustable, direct current, regulated power supply when built with all the soldered components. Table 1 highlights the properties of the circuit board and solder. Experimental measurements. So harmonic and random vibration testing were done for each of the four phases of the circuit board. LabVIEW 2018 was the software package used to either generate a pure sinusoidal or band-limited Gaussian white noise. This digital signal was converted from digital to analog using a DAC, and this was then sent to an electrodynamic shaker. The shaker is rigidly connected to the geometric center of the PCB. Vibration measurements were taken off with an accelerometer. This accelerometer sent the signal to another DAC, which converted the analog signal to digital, which was then sent to LabVIEW to store and process the data accordingly. So figure 1 shows the four phases of the printed circuit board used throughout this paper. Figure 2a shows the vibration, excitation, and measurement schematic. Figure 2b shows the measurement location on the PCB reference to XY coordinate system. Finite element modeling. Firstly, the finite element models are generated for the first three phases shown in figure 1a to c using ANSYS Mechanical APDL 18. The bare circuit board and solder material which fills the board's penetration are modeled using Shell 181 elements. The copper leads and surface mounted components are modeled using solid 186 elements. The boundary free conditions of the circuit board are such that the outer edges are all free. The diametric penetration, which is rigidly connected to the shaker, is treated as being completely fixed. The excitation induced by the electrodynamic shaker can be simulated in the finite element model as either harmonic or random based displacement. This is figure 3. The finite element models of the circuit board and its surface mounted components. Results and analysis. Figure 4 here shows the resonant curves of the circuit board in phase 1, both experimentally and numerically obtained. The Bay printed circuit board had a signal dominant resonant frequency in a range of 0 to 1000 Hz. The resonant frequencies obtained both experimentally and numerically are normalized for comparison and are shown in figure 4. The agreement is generally good and the percentage difference between the resonant frequency is 1.56% as shown in table 3 here. The damping ratio of the mode is calculated to be 0.02. Natural mode shape of the bare printed circuit board can also be visualized experimentally using Chladni's patterns as shown in figure 5a, and figure 5b compares it to the numerically determined mode shape, which shows a good agreement. The frequency response of the phase 2 and phase 3 configurations are shown in figures 6a and 6b respectively. The agreement between the experimental and numerical data are good for both boards. Table 3 indicates that the percentage deviation between experimental and predicted resonant frequency for both boards are 3.24 and 1.79 percentage respectively. Phase 2 shows a decrease of 3.6% in natural frequency compared to the bare circuit board, whilst Phase 3 had a substantially larger increase of 74%. The damping ratio of Phase 2 board increases by 50% to 0.03 and reduces by 65% to 0.007 for Phase 3 board. Now, the relatively small change in natural frequency from phase 1 to phase 2 is reflected when comparing the mode shapes of figure 5b with that of figure 7a here, which shows they are generally similar for both phases. A more pronounced change associated with phase 3 compared to phase 1 is observed by comparing figure 5b with that of figure 7b. The subsequent analysis indicates that the surface-mounted components and the associated solder joints have a significant effect on the dominant natural frequencies, mode shapes, and damping of the overall PCB. The effect of the solder material alone is investigated in phase 4. The solder material itself is denser and stiffer than the bare circuit board. It is evident that the solder decreases the natural frequency by 6% and the damping ratio reduces from 0.02 to 0.014. The increase in mass due to the solder material dominates the increase in localized stiffness, therefore reducing the value of the natural frequency, as can be shown here in figure 8, showing the phase 1 PCB and the phase 4. In instances where PCBs are subjected to broadband random excitation, knowing the resonant frequency and mode shapes are important in predicting the average response levels. The bar charts in figure 9 show the ratio of the measurement points relative to point 3. The numerically generated results are presented alongside the measured values. There is good agreement between the experimental and numerical results, thereby further validating the finite element model. Conclusion. Firstly, for boards with a small number of solid components, the mass effect dominates the stiffness effect and the natural frequency is reduced compared to a bare circuit board. The mode shapes of the boards are also shown to be almost identical. Secondly, for a board with a large number of solid components, the increased number of localized stiffness points dominates the localized mass effect and the natural frequency increases significantly. The mode shape for the densely populated board also differs significantly from that of the bare circuit board. Thirdly, experimentally, the effects of the solder material reduces the resonant frequency of a circuit board. And lastly, the study generates finite element models for 3 of the 4 PCB cases studied, and there is good agreement with the experimentally results obtained. These are some of the references utilized in this paper. Thank you for watching this pre-recorded presentation. I hope you enjoyed it, and I am now open for your questions.